So in chapter 5, we're going to cover the network layer. So the network layer exists in the stack as layer 3. So this network layer is layer 3, and it uses, as we talked about before, it uses IP version 4 or IP version 6. We're going to cover mainly IP version 4 here. We're going to talk a little bit about IP version 6. Although in CCNA version 5, there is a whole chapter about IP version 6, because the trend is going towards IP version 6, and we'll discuss why. So as we have discussed before, in the encapsulation, the IP header, which we will talk about, is encapsulated in the IP header in layer 3, and it gets sent down in the stack, as we can see. So this header is composed of many fields, and we'll talk about how each field is being used. The network layer is used to facilitate the end-to-end communication between two hosts, two end-to-end hosts, or two subnetworks, okay, or two networks, okay. So so each host will have a unique IP, as we said before. So each of these hosts will have a unique IP, and the network layer will be used to facilitate the communication between these two end-to-end hosts, okay. Similar to all the other layers, in the network layer we have a distinct address, and here we have again 32-bit IP address for the source and 32-bit IP address for the destination. And as we said before, we always have to have in each packet the source and destination addresses. The layer 3 IP addresses uses 4 basic processes: the addressing, encapsulation, routing. So these are the main functionality of the routing protocol. The routing protocol uses some kind of addressing. It uses encapsulation and decapsulation like any other layer, and this is part of the reference model. And the main functionality in the network layer, which really distinguishes the network layer from any other layer, is routing. Okay, so this is what we are going to cover in this chapter and next chapter as well. Okay, so as we said before, the addressing, you have to have the source address and the destination address, because in each transmission you have to have an acknowledgement, some kind of acknowledgement, or a receiving packet that corresponds to the transmission packet. So therefore, the source address will indicate the transmitter IP address, and the destination address is the target host IP address. On the way back, these two addresses are reversed. Okay, so that's it's easy so far. Nothing is new. So this is the encapsulation decapsulation process. So assuming that I want to send data, so what will happen is that the host will form all these different headers from different layers all the way up to the physical layer. So when we send this frame, the frame will go to the next router. What the router will do is that the router deals with this part as an abstract unit of data. It has layer 2 and it has layer 3. It has layer 2, which means that it will extract these two, header and trailer, and will throw it away. It will understand that the physical address is its own physical address, so it has to send it up to the routing layer. In the routing layer, it will read the IP packet, and then it will process the header, and as we will see later, it will have to process and interpret each field in the header to know where the IP address is, how am I going to deliver it. It may have to consult or refer to the routing layer to know how the packet will be delivered to the next router. And then after that, after processing the packet, it will have to push it down again in the stack, which means that the layer 2 header and trailer will be regenerated. And as we said before, as part of this process, the destination and source physical addresses will have to be changed, right? Because the destination physical address will be the physical address of the next router, right? And so on. And I will keep doing this again and again for each router, all the way to the final stage. When it arrives to this end or target host, the host will check the physical address. It finds that the physical address is its own. It sends it up to the routing layer. In the routing layer, it will check the IP address. It finds again that the destination IP address is its own. So in that case, it doesn't have to forward it or route it or do anything special about that. So it sends it up in the TCP or transport layer header. The transport layer header will have to send this particular data to the target application. How does it know that? From what? From the port number. So from the port number, it knows that it has to put it in the buffer of this target application. That's part of that transport layer. And then it goes to the application where HTTP or any kind of application layer protocol can read the header and display it on the screen. So that's the sequence. So when the packet arrives at the destination host and is processed at layer 3, the host examines the destination address to verify that the packet was addressed to this device. So in every layer, I have to ask myself, is this address my IP address or my physical address? If the answer is yes, then after processing, I have to push it up in the stack. Okay, so that's the general rule. If it's not my IP address, then I have to do something about it. If I'm a router, okay, then I have to consult the routing table to send it forward. If I'm a host and this packet arrived to me by mistake, then because the destination address is not my IP address, yet I have kind of received this packet. What do? Ignore it, just discard it. Because I'm not a router, I cannot route it further. I'm not a router, I don't have any routing table. The host does not have any routing table, only routers do. Okay, so in that case, I can discard it.
Doctor, now, for example, anything that we send from our host, from our computer, for example, or our phone, it goes to a router, and then another router, and then another,
right,
until it reaches the destination?
That's a good question. So as part of this, well, what if the packet actually gets lost? Does it have to circulate forever? Or there has to be a limit? So it may actually go and like when you drive your car, you're going someplace, but you don't know the directions exactly. So you get lost. So, well, what will you do then? You keep circulating, you keep going here and there, but there has to be a limit at which you will just give up and say, let me go home, right? So in other words, in our case here, the packet will not go home. The packet will well, it depends if the router sends it back to the source, or the router may actually discard it. Okay, unfortunately, we don't have to be discarded in real life, but the packets can be discarded easily. Okay, and what does that mean? Well, if the packet is discarded, that doesn't mean that the packet is lost forever, right? Because we have TCP. TCP reliable will retransmit it again. And hopefully the next time it will be delivered correctly. So that's why we have to have, multiple protocols in each layer. Each one, they work hand in hand. So if one loses or if one does anything strange, the other protocol will complement it, will complement its functionality. Okay?
So we will build again the IP header in this case. If it's lost and then it's still in the TCP, we will build the IP.
Yes, exactly, of course. If the host tries to retransmit it, it will send it down in the routing layer. The IP address will have to be inserted again in the packet and so on. Okay? So routing. routing, as we said before, the good thing is that in the first 2 chapters, we have kind of given you a full picture all at once, right? So here, we'll just, just spotting or putting some lights, we're shedding some lights on some parts, and then we'll talk about them deeply. But the global picture should be in your mind by now. So routing is simply by examining the destination IP address, we go and check the routing table. The routing table will have simply, it has more than 2 columns, of course, but just for simplification here, we have 2 things. We have an IP and we have a next hub or next forwarding router. Okay, based on the destination IP address, I have to consult the routing table. I look at all the IPs one by one, and then once I find this IP, I know that the next hub, which indicates that I'm in a big intersection, okay? And depending on the IP, depending on the signs in this intersection, I'm going to Al-Khor, then you have to go to this direction. You're going to Al-Wa'b, then you have to go to this direction, and so on. So that's what the routing table will tell me. Okay? So the routing table is much more complicated than that, of course. We'll talk about some details related to the routing table, but luckily we don't have to cover everything in this chapter. Okay? This course in general. So these are some of the protocols existing in the network layer. We have IP version 6, IP version 4, and IP version 6. And then we have IPX and AppleTalk and some other protocols. These protocols are not used anymore. So they all lost the ground to IP. Okay? So IP version 4 is the predominant protocol by far in the network layer. Even cellular networks and all the networks that did not support IP version 4 when they have been first designed, they kind of converged through using IP later on. So nowadays, all the networks, all types of networks, even cellular networks, they use IP one way or another. Okay, so but then we have some problem with IP version 4, which we will talk about, based on which they have to converge, or they have to like update or upgrade to IP version 6. Okay?
Now the computer has to, when we see the IP config, we have two versions of IP. We have the IP version 4 and IP version 6.
Right. But yeah, most probably IP version 6 is not used unless you are running a special service that uses IP version 6. But in normal operation, we usually use IP. Okay? IP version 4, yeah. Okay? So the basic characteristics of the network layer are as follows. First, the network layer is connectionless. That's different from TCP. So since TCP established an end-to-end connection, we don't have to repeat again and do it in the network layer. So the network layer, it waits for a packet. It uses the packet as an independent unit. It does not relate this packet to a specific connection end-to-end. It doesn't have any end-to-end kind of picture. Okay, I'm only receiving a packet, consult the routing table, and then send it to a specific direction. So for me, this does not guarantee the ultimate delivery at the end. So when you find a sign in the intersection to tell you go to this direction, that's not a guarantee for you that you will reach to the ultimate destination, right? So you may go to the next street and then get lost. Okay, so it's not my problem. It's not the problem of this particular intersection, right? So therefore, the network layer is connectionless. I don't have to establish a specific connection between my router and any other router. I don't have to have this connection. And it's best effort in the sense that it's unreliable. So if I send it to a router and the router and it does not reach to that router, I will not send it again. I don't have the concept of timeout. I don't have timeout. So if it doesn't reach and I don't receive an acknowledgement, it's fine. I will just rely on higher layer protocols to take care of that. So I don't have to perform retransmission within two routers. The retransmission happens once end to end in case you're using TCP or in case you're using any reliable protocol at the transport layer. Okay, so it's connectionless. I don't have to establish a connection. It's best effort, which means unreliable. I will do my best, but there's no guarantee. The other thing is that it's media independent, and that's a very important characteristic here. I don't care whether the medium is fiber optics or wireless or anything like that. Okay? All I need is to know a specific parameter which we will talk about. So I only need to know one parameter which is kind of dependent on the medium, which we will talk about. But other than that, other than this parameter, I don't care whether it's fiber optics or wireless. I don't have to do anything special. This is one of the problems, for example, when it comes to using, for example, TCP or specific IP over wireless. Through some research, people have discovered that TCP behaves very badly when it comes to wireless, because wireless tends to lose packets every now and then, and TCP deals with this kind of loss in a very weird way, and doesn't pay attention to the fact that this is wireless. It may go up and down in a very short time. It doesn't do that, so it performs badly. So, but that's the price that we don't have to pay, that we don't need to know whether we're working over wireless or wired or anything like that. Okay, so we don't have to have any dependency between the higher layers and the physical medium. So that's kind of an advantage, or in a way it's good, because having this kind of dependency complicates the protocol quite a bit. So until recently, people did not have to address this, but later on, through some research and by the evolution or the proliferation of using these protocols over different types of wireless networks, we have Bluetooth, we have Wi-Fi and things like that. People have started to discover some issues when it comes to using higher layer protocols like TCP or something like this over wireless. So they started to propose some new solutions to address this through using a different version from TCP. But that's outside the scope. Here, what we're talking about is that these protocols, either TCP or IP, are totally medium independent. They don't have any idea whether the medium is wireless or wired or fiber optics or anything. Okay, so this explains the concept of connectionless. So unlike TCP, which is connection oriented, and UDP, which is connectionless, IP is similar to UDP in the sense that it does not have to create an end-to-end connection. Okay, similar to sending a mail. When you send a mail, you don't actually ask the other side, are you able to accept this or not? You just send the mail, and then if it reaches to the other side, then it's fine. If it does not reach, then if you have a source address, then you may be lucky and receive it back again, in which case you can send it and modify the address. So the media independent, it's the responsibility of the data link layer to take care of sending IP packets over the different types of media, which we will talk about in later chapters. So data link layer is medium dependent, of course. But IP does not have to deal with that. IP does not have to deal with specifics of the type of the medium, whether it's wireless or wired or fiber optics and stuff like that. The only exception to this, okay, is what we call fragmentation. And fragmentation is similar to segmentation or segmenting. Remember we talked about segmentation in TCP or in transport layer in general, right? Here we have a similar concept that if the segment itself that we're trying to send, okay, is a little bit larger than what I should handle over that particular medium. For example, if you have maybe fiber optics or something like this, you may be able to deal with a little bit larger fragments. We call them fragments, not segments. Okay, in which case a segment will be a fragment and will be sent right away. But for other types of medium, maybe such as wireless, maybe the limit of the fragment is a little bit shorter. Okay, in which case one segment will correspond to 2 or 3 fragments. Okay, so in that case the network layer will have to do this fragmentation. Okay, so the fragmentation is based on what we call maximum transmission unit. That's one parameter that I need to have in the network layer. Okay, this parameter, the data link layer sends it to the network layer. The data link layer will have to send it to the network layer based on its knowledge about the medium. But again, it's just one parameter. It's a pre-configured parameter in IP. So whenever I receive a segment, I compare it with the maximum transmission unit. Am I able to send one segment in a maximum, which is less than the maximum transmission unit? In which case, I send this segment as one fragment, and that's it. I don't have to do anything special. Otherwise, I have to get the segment and divide it into 2 or 3 or 4, depending on the maximum transmission unit. And I have to deal with it, which means that I have to do fragmentation and defragmentation. So, so I have to fragment and send, and then I have to defragment in order to get the segment again. Okay?
Defragment in the router.
At the router, yes, but we'll see at which router. Okay? But now it's at one of the routers. Okay? But it has to be done before sending anything to the TCP.
Okay.
We agree on that?
Yes.
It has to be done before sending anything to TCP. So before sending anything to the higher layer, I have to defragment and get the original segment in order to send it as one unit to TCP.
Is there error detection in the fragmentation?
That's a good question because you may actually use one fragment in the middle of the packet. So in one segment you fragment it into 3 fragments and then you send. So one fragment arrives correctly, the next one gets lost, the third one gets arrived correctly. So what do I do in that case? We'll see. Okay. In general, we said that IP is unreliable. There is no error kind of detection or reliability. We'll see that. So, so this is the maximum transmission unit. So in the segment from TCP, we have the data part, right? And we have the header part from TCP, and we have the header part from IP. If you remember, we said that the minimum size of a TCP header is how much? 20 bytes. If you remember, it's from 20 to 60, right? So the minimum size of the TCP header is 20. Okay. So the TCP over IP over Ethernet. Ethernet is the data link layer protocol or standards, okay, to deal with wire, and particularly UTP and STP, unshielded twisted pair, the wire. You will talk about that, or maybe you talked about it already in the lab. So, which is the normal network cable that we have at home, the normal with RG45, and we connect it to the router. So the maximum transmission unit for Ethernet is 1500 or 1500 bytes. Okay? Which means that in that case, the maximum segment size is 1500 minus the IP header minus the TCP header. The TCP header is 20 bytes, and as we will see in a minute, that the IP header is also 20 bytes. Okay? So if the maximum transmission unit from Ethernet is 1500, this means that the maximum segment size from TCP point of view is 1460. Okay? 1500 minus 40. Okay? So that's what this explains. So if I have this, then I don't have to do any fragmentation. If the maximum segment size is 1460 and I'm sending over Ethernet all the way, and I stressed on all the way, which means that every single hop from one router to another is similar. And it's Ethernet all the way. So if the application generates segments with that size, uses TCP and IP, and send it to the next router, which happens to be over Ethernet, then I will not do fragmentation. Then the next router will have to do the same. If it uses Ethernet, then good news, I don't have to do fragmentation. And I do like this all the way. Okay, so this is the happy path. But is this the case for everything? Of course not, because end to end I may have to go over submarine cables and then go and then it happens that I have to go through wireless, and so for each router, the router will have the maximum transmission unit for that particular link. So when it tries to create the fragments over this particular link, it has to ask itself, is it the same type? If it's not the same type, is it less or more? If it's more, again, good news, I don't have to do anything. If it's less, then I have to do fragmentation. I have to do fragmentation. So when a host usually initiates the TCP session with the server, it negotiates the TCP segment size. Okay? So it has to negotiate the TCP segment size. If the segment size is 1460, which means that the maximum transmission unit is 1500, then it creates the segments based on that. Okay? So I'm setting myself to have no fragmentation from the host point of view. But is this enough guarantee? Of course not, because I have to go through multiple types of networks as I go from end to end. Okay? So the value of the maximum segment size field is determined by the maximum transmission unit configuration on the host. It's configured on the host that this host on this particular network card uses Ethernet, which means that the maximum segment size is 1460. So I will generate, so the application sends me a file, I have to segment it using a segment size of 1460, right? So I have to divide into segments, each one is 1460. So for each segment, I have to put a TCP header and send it down. When the IP finds the TCP header and the data, it will create the IP header, and then it sends it to the router. Okay? The problem happens at the router. The router has to adjust itself to the next medium or to the next type of network. That's what will happen now. So the default Ethernet maximum transmission unit in case is 1500 1500 bytes, 1500 bytes. So the IP header, this is what it looks like. So of course we have the source address and the destination address. Each of them is 32-bit, similar to the port number. We have the destination IP address is 32 bits, but here we'll see that the format of the IP address structurally is different. Okay, it has certain characteristics which is totally different from the port number. The IP source address is also 32 bits. Okay. When a packet is first generated, the value is entered into the TTL. The TTL is what we call the time to live. Okay, this refers to the point that you mentioned before. The time to live is the amount of time that this packet is allowed to live in the network before it reaches to the ultimate destination. Okay, this is the time that you can afford yourself that, you know, when you get lost, I have to keep circulating for a certain amount of time. After this time, I give up and I say, okay, I'm lost, I cannot get to this destination, I have to discard or I have to go back to the sender. Okay? So this time to live is simply a field which gets generated initially by the operating system. Okay, it's a default value in the operating system. Most probably Windows, when it creates any IP header, it puts in the time to live, I think 265 or 256, I think 256. 256, it indicates that it can live for 256 routers before it dies. Okay, so if it goes over, a route and then it keeps circulating, okay, for each router it kind of subtracts 1 and it keeps going down, down, down until it reaches a router that finds that the time to live is 1. If the time to live is 1, it subtracts 1, which means it's 0, then it discards the packet. Then this packet must be lost in the network. I have to. Otherwise, we can find, networks with, packets from 1,000 years ago or something like this, which doesn't make any sense. So the packets, after some time, they die. Okay.
But here it's written that TTL field was the number of seconds.
Yes, that's a misleading point. So when they have first designed TTL or designed the IP header, they said that this is the time that the packet is allowed to live, the time in seconds. Okay, but later on, they have actually used this TTL field. They kept the name as TTL, however, it's used as the number of hops. Okay, it's used as the number of hops. So it's not a timestamp in particular. It's actually a number of routers, because they found that it's much easier a technique to have each router subtract 1 and that's it. Okay, so it's much easier compared to dealing with timestamps. Okay. So this is the time to live now is set to a specific value which gets decremented, okay, by each router. So the operating system at the host creates or generates time to live based on some default value. It's not complicated in the sense that I have to kind of estimate how many hops and no, it's by default. It's a pre-configured thing. So Windows puts, I think, 256. Maybe Linux uses maybe 60 or something like this, 65. So these are default values are based on some experiments. These are not based on any prediction techniques or something like this. So it's simple. Yeah, here are the numbers. So Unix uses 255, Linux uses 64 or 255, Windows uses 32. We don't have to memorize these numbers, of course, but these are default values for this time to live thing. So the important thing here is that each router will decrement this TTL number by 1. Okay? Or if it decrements it by 1 and then it finds that it's 0, then it simply drops the packet. Okay? It drops the packet. And this happens at every single router. So, and eventually the packet of the TTL which reaches 0 is okay. So, so there is a protocol field here, which again is 2 bytes. Okay, so we talked about, so far we talked about source address, destination address, and we talked about the time to live. We also talk about here the protocol field. The protocol field can be one of these 3. What happens is we have the stack here in terms of layers, right? So we are in the network layer here, and this is IP, right? So this is layer 3. So now I need to send it up in the stack. Okay? So send it up to where? Remember that these protocols are designed as services that run as software services that run either in the host or in the router or something like this, right? Or maybe embedded software that runs on a microcontroller or something like this. So in any case, this protocol has to send it up in the stack, which means that it has to send it to one possible service or protocol. And remember, this is layer 4, right? This layer 4, there could be here TCP, there could be UDP, there could be anything. Right? So how would I know whether this packet should be sent to TCP or UDP or to where? Remember, we did the same when we talked about transport layer. We said that the transport layer will send it up based on the port number. So we did the same in a way, using the address or the port number. Here, we have the address to indicate the ultimate host or the destination, right? But we need to still have something to tell us which protocol in the next layer I should use to process the data or the payload itself. Okay, and that's the function of the protocol field. So the protocol field will tell us that the upper layer protocol that's responsible for processing this packet is either ICMP, we'll talk about it later, or TCP or UDP. Or it could be any other transport layer protocol, okay, which is not in this list, in which case it will have a number. So luckily here I have 2 bytes, which means that I could have up to 2 to the power 16 different protocols running in the transport layer. Okay? I could have up to 2 to the power 16 different services, and I can send it up in the stack to any of these protocols, right? So that's what the protocol field is used for. So we'll stop here, and next time we'll start with the type of service. So the last scenario we're going to talk about for sliding window mechanism is the accumulated acknowledgement. We talked about the fact that the acknowledgement by default says that I have received everything up to this point correctly. Please send me the next one. And the next segment will be highlighted in the acknowledgement number. So this scenario talks about the fact that when we lose one acknowledgement, the other acknowledgement or the following acknowledgement can supersede or like override the last one. So the scenario here is that the server sends one segment starting from sequence number 92, and with 8 bytes, the next one will be 100. So here, unlike the previous scenario where the timeout was premature and much smaller than what it should be, much larger than or much greater than what it should be, here the timeout is small enough. So because the window size is 16 bytes, or in other words, the window size can fit 2 consecutive segments. So the server will send one segment, and then based on the window, it sends another segment without having to wait, unlike the stop and wait. So after it sends the second one, then the window has elapsed, or I can send 2 segments without having to wait for acknowledgement. So in that case, ideally, the client will send an acknowledgement so that the server can slide the window and send other segments, right? What will happen is that, or assuming that what happened now is that the acknowledgement was lost. Well, here, it depends on the timeout. If the timeout is up to this point, for example, okay, then what will happen is that the server here will time out and will try to send this segment once more. So this segment will be sent again here. Okay? So it all depends on the timeout. Here in this particular scenario, however, this did not happen. What happened is that the timeout is large enough, okay? And it happened that the first acknowledgement was lost, but the next acknowledgement arrived to the web server before the timeout. Okay? In which case, what should the server do? It will continue sending other segments. So starting from here, it will slide the window for how many segments? For 2 segments, bravo عليك. So the server here will slide the window for 2 segments, which means that it will send, starting from here, it will send another segment with sequence number 100 plus 20. برافو عليك، صح مظبوط. 120 بالضبط. That's true. 120. So that's so even though we have lost one acknowledgement, but that did not affect the delivery in any way. Okay? It may have slowed it down a little bit, because if this acknowledgement had arrived here, this will allow me to start sending the next segment up from this point. So if this has arrived, then I will start sending from this point as opposed to this point. So it slowed down a little bit, but at least nothing abnormal happened. So even though we've lost an acknowledgement, but it did not affect the transmission that much. So the performance is still almost the same. And this is the benefit of accumulated acknowledgements. Okay, so that's the main benefit of accumulated acknowledgements. Okay, so I think this is the end of chapter 4. So today we are going to talk about the network layer, or chapter 5. Okay.